takes us away from limits a little bit, away from derivatives a little bit. Okay. And we go into integrals eventually. Okay. Not today, but eventually that's where we're headed. So, we're going to, in this unit 1, take a look at the relationship between the graph of a rate of change function and the area of the region between the derivative graph and the x-axis. So we talk about rate of change. Rate of change is what we did last semester. So rate of change being the derivative graph. And then the area of the region between the derivative graph and the x-axis. Well, that's what we're getting ready to learn. That is the integral. So that's what we'll learn here within the next week or two, is we will start learning the idea of integrals. Okay? So, but today is more looking at the relation and starting to talk about area under a curve and ways we can do area under a curve without using the idea of an integral yet. So, we're going to consider the tropical cyclone Imelda that brought more than 40 inches of rainfall over a 72-hour period in southeast Texas during September of 2019. We're going to go through some questions here. So, scenario, the background. In order to avoid floodwater entering your home, you rent a pump that can remove water at a rate of 500 gallons per hour for the first 8 hours of pumping. As the storm grew stronger, you got a second pump. And for the next 16 hours, you could remove 900 gallons per hour using the 2 pumps. Okay. So, 1A, ask us to draw a graph that models the removal of stormwater from your property. Label the axes correctly. Okay. So, think about what we're graphing here.
Hours go on the x-axis and then gallons go on the
I definitely agree. I'm going to generalize time. But what is this time measured in?
hours.
In hours. Okay, so generally, oh, I was going to blow this up. Oh, well, I'll work with it as is. I'm going to work with it as is. So this is my time axis, right? Whether you label it as time or t or whatever, but it's in terms of hours, okay? Now, along the left, we're not...
Floodwater, measured in gallons.
Yeah, okay, so I had to look and see what I had, sorry. So I have it labeled as gallons of stormwater. So stormwater in terms of gallons, but gallons of stormwater is what I have it listed as here. So I'm not the only one that I felt like my handwriting was a little rough this morning.
No, I filled out an application for shadowing and it was pretty rough.
Okay, so I'm going to call that, I don't think it gives it here, but I'm going to use G of T to describe that, representing gallons. Okay, so what do we know? You rent a pump that can remove water at a rate of 500 gallons per hour for the first 8 hours of pumping. Okay, so from 0 to 8, what's happening? We're removing 500 gallons per hour. And so we're going to actually represent that. Did I get that the right spot? Yes, kind of. Okay, we're going to represent that as a straight line because that's representing that, what is it, each hour, right? So at 1 hour, it's 500 gallons. At 2 hours, it's 500 gallons. At 3 hours, all the way up to, at 8 hours, it's 500 gallons, yes? And then what happens?
Then it goes 16
To
900 for the next 16 hours.
For the next 16 hours, we're going to have 900 gallons. So we're going to be doing 900 gallons up to where? Okay, so if we're doing 8 plus 16, that's going to be up to 24 hours.
So it starts on 8, right?
What?
It starts on 8.
Yes. Because, so basically, it was 500 gallons per hour from this during the 7th hour up to the beginning of the 8th hour. Well, or first 8 hours of pumping. Should I? Yeah, because you have 0 to 1, 1 to 2, so then 7 to 8 is the 8th hour. There we go. And then, 16 more hours takes it to 24. Okay, so, and I kind of have mine, and this has to do with what we're getting ready to do next. Maybe I shouldn't have done that yet, but I kind of have mine as that, just some dotted lines to help us figure out the rest of this next part. Sorry. So B, when we say area under a curve, this represents the area between the graph and the horizontal axis. Find the area under the graph from 0 to 8 hours. What does this value represent in context to the tropical storm Imelda?
4,000.
Why 4,000?
500 times 8.
Okay, because what's going on here? This is 500 gallons per hour for how long? For 8 hours, right? That's what's happening in that section right there. And so when you do, 500 times 8, you get 4,000, right? So that's the area under the graph from 0 to 8 hours.
So it's kind of like an array.
It's kind of like what?
An array, like a little bit. Maybe that's wrong. I don't know.
I'm not understanding the word array.
The thing with the side. I'm sorry.
No, you're fine. I'm not, that word's not coming to mind for me. And so that's why I'm trying to connect with you, and it's not.
Okay then. Maybe that was a while ago, but I like in a array.
In a math context?
Yeah,
I'm not there.
where
I'm
it's
sorry.
basically just area.
Just shh.
No, it is area.
I'm
I
sorry,
mean,
wait.
yes, it is area. So
I'm sorry.
now, answer this last part. What does this value represent in context to the tropical storm Imelda?
4,000 gallons after 8 hours.
Yeah. A total of 4,000 gallons of storm water was removed during the first
8 hours.
8 hours.
8 hours of the storm.
So
Okay.
it's almost like what the lesson was. We had a little quiz and it was like sliced in. Remember, you did like yeah. Like when
Well, you're trying to figure out the wording.
Yeah.
And that's what some of this is today. Yes. That's what some of this is, right? So, what?
I forget what it's called already.
Reviewing a new row.
Oh, yeah. Okay, so write something in here. I don't have as much room since I didn't enlarge this area, but a total of 4,000 gallons of stormwater was removed during the first 8 hours. Do I want to say anything else? I guess from the first 8 hours of the storm. Okay. Find the total area under the graph for the entire 24-hour period. Explain the meaning and context to the scenario.
So 900.
900 times 16.
This is 900 gallons per hour over the course of 16 hours. So we have to do 900 times 16. Mm-hmm.
In that framework.
Is this the answer to this question?
No, you have to add in the 4,000.
Yeah. Plus the 500 times 8 for the first 8 hours. So you're adding in the 4,000 for a total of... That math was a little easier, right? 18,400? Okay. Explain the media in context of the scenario.
18,400 gallons was pumped after 24 hours. Remove pump.
Okay. And I wouldn't, well, I guess total at the end of 24 hours, but during that first 24, or during that 24 hours, right? So mine reads, in 24 hours of pumping stormwater during Imelda, a total of 18,400 gallons of water was removed from the property by the pumps. So, the gist, okay? You guys,
Can we just like copy the top one?
sure. I'm going to say during the entire 24-hour period, 18,400 gallons of stormwater was removed by the pumps. Okay. Right there, we're starting to talk about area under a curve. That's going to be the theme this semester. Slope of the tangent line was the theme first semester. Area under the curve is the theme this semester. Okay. Didn't I? No, I didn't. Not on this page. Okay. So, we're going to talk about finding area using Riemann sums. Okay. Again, this is a lead into integrals eventually, but finding area using Riemann sums. In other words, if we're trying to find the area under this curve, this isn't a rectangle, is it? Okay. So we can't just, oh, okay, well that's, it wasn't as easy as the 500 times 8 or the 900 times 16. This is where our Riemann sums come into, okay? So, as I mentioned, two big ideas in calculus are the tangent line problem, what we spent first semester doing, and now the area problem. In the tangent line problem, you saw how the limit process could be applied to find the slope of the tangent line, thus the derivative, right? The second classic problem is finding the area under a curve that is bounded by the graph and the x-axis and any two x values. So, a basic overview of areas as limits. In the limits of rectangles approach, we take the area under a curve above the interval a to b by approximating a collection of inscribed or circumscribed rectangles in such a way that the more rectangles used, the better the approximation. Finally, the number of rectangles is increased without limit, and bingo, we get the area, now known as integration. Specifically, we're interested in finding the area of a region bounded by the x-axis and the graph of a non-negative function defined on some interval. Okay, so the idea here, okay, this is broken into rectangles. We're basically going to be finding the area of the rectangles and adding them up. Is this going to give us a very accurate area? Not really. Okay, now what happens? The smaller the rectangles get, the more rectangles you get, the more accurate it becomes. And that's where then the limit, okay, as x approaches infinity type thing, that's where the limit comes into play. Okay, so right now though, we're doing this by hand, and we're looking at different options. So this is our Riemann sums here. I think it's the next page where we, start talking about the different types of rectangles we could have. So let's look at example 2 to kind of break us in. Okay. Consider a 30-gallon aquarium is being filled with water at a rate modeled by r of t equals 6 sine of pi over 8t. That's that curve there, where t is time in minutes and r of t is gallons per minute. Find the volume of water in the tank after 5 minutes by using 5 rectangles that are 1 minute wide and r of t in height. Okay. So, r of t. This function represents r of t here. Okay. We want the volume of water in the tank after 5 minutes, so we're going from 0 to 5, which is why you don't see any rectangles past that.
Okay, that's what I was just gonna ask. I was like,
There's no
does that
rectangles?
mean at 5 it was fully filled, but that's no.
No, because we're trying to figure out how full it is at 5 minutes. It's not necessarily fully filled, but we're just going from the interval from 0 to 5. Okay? And so, yeah, that is only after 5 minutes. And we're going to use these 5 rectangles. So basically, we have to find the area of each of the rectangles and add them up. Now, I'm going to make us a chart to organize. You might want a calculator. Let me rephrase that. You want a calculator. Forget the word might. Unless, of course, you're going to do the math of 6 sine of pi over 8t in your head on 1, 2, 3, 4, and 5.
Sine of pi over 8. Don't know.
Exactly. We're already stuck at pi over 8.
Times 2.
So,
Overcharged.
Oh no.
okay.
That's a bad start. That's sad.
It's really dead if it won't even turn on.
During the calc test, it kept turning on and off, and I was like, ooh.
That's when you just walk over and get a different calculator.
Mm-hmm.
So.
I didn't use it enough though, so.
Okay, so T, we're doing after 5 minutes, we're using 5 rectangles. So we're using the rectangle that goes from 0 to 1, 1 to 2, 2 to 3, 3 to 4, and 4 to 5. So as we look at this first rectangle that goes from 0 to 1, where does it intersect the curve? In other words, what I'm looking for you to see, do you see that it intersects the curve right there? Okay, so I'm looking at where that corner of the rectangle on the curve is. Where does a piece of the rectangle hit the curve? And it's that corner of the rectangle, yes? And that is when t is what value? That is when t is 1. So we're going to use t equals 1. How do we find the r of t value when t equals 1?
That.
You plug it in. Okay, so you're going to take 1 and plug it into 6 sine pi over 8t. So what is 6 times the sine of pi over 8?
Can we plug it into our y? Y1.
Oh yeah, you could.
Then you can do y1 parentheses.
Uh-huh,
Okay.
yep. Valid question, or valid point.
Oh, Kylie was
Did
thinking
you guys
today.
understand what she was saying? If you don't want to type the same equation 5 times, plug it into y1 and then use it. I feel like I've taught that better this year. I feel like that's something that is stuck this year. Okay, I have mine written down to 3 decimal places.
2.296.
So at this point, after one rectangle, what is the total area? 2.296. Okay, next rectangle. It's red on my paper. Where does it intersect the curve?
2.
At 2.
Oh.
So we're going to use t equals 2, yes?
4.242. 2.425.
4 point what?
4.243.
There we go.
Shut up.
Okay, and then what is our total area at this point?
8.485.
Disagree?
Wouldn't you just add them together?
Yeah.
6.
Oh, never mind.
You add them together?
6.539.
For the total area.
Why are you adding
Or total area you added.
Because we have the area of the blue rectangle plus
Oh.
the area of the red rectangle.
We learned that in algebra.
I'm
You learned that before algebra, I think, but
Sorry.
This is why you gotta be.
it is.
okay. What about the yellow rectangle?
3.
5.543.
Okay. It intersects at the right corner. Notice these are all intersecting on the right corner, aren't they? And that's the design of these rectangles on purpose. Okay, and we'll talk a little bit more about that in a moment. What was 3?
5.543.
And if we add that to our running total,
12.082.
what about 4? Or what about the the next rectangle?
6.
It intersects at 4. It is, I have written on mine 6.000, but it's 6, right?
18.082.
If you add 6 onto the 12 number, 18.082. And the last rectangle, where does it intersect the curve?
5.
At 5. And what is the height of that rectangle?
5
add it on to my running area.
$23.625.
Okay. Now, keeping in mind that this column was in minutes, right? And then this RFT was gallons per minute, because RFT is measured in gallons per minute. What do we know? The question was, find the volume of water in the tank after 5 minutes.
There's 23.625 gallons.
Okay. After 5 minutes, the aquarium has 23.625 gallons of water in the tank.
That makes sense.
On my notes, I have it written in here. I don't, BenQ dilemmas here. So after 5 minutes, the aquarium has 23.625 gallons of water in the tank. Okay. Now, as we look at these, and we'll talk about, I think it's top of the next page if I recall. Yeah, we'll talk about the various rectangles. But these rectangles are right-hand rectangles. Because which side of the rectangle did we use every time? We use the right-hand side of the rectangle. Okay, because that's every place that it, that was the design of these rectangles. These rectangles were drawn to intersect at the right-hand edge of the rectangle. Okay. By using more rectangles with smaller widths, we could achieve a better approximation. Okay, so you put more rectangles, we get smaller widths, we get more accurate pieces here. In fact, if we consider taking this to a limit of accumulating an infinite number of rectangles, we would arrive at the exact volume of water in the aquarium after 5 minutes. This is called the definite integral and is represented by this notation at the bottom of your paper. So that little squiggly is what we're eventually going to know as an integral sign. Okay, it's not a squiggly, it's an integral sign, but,
And
for
so
reference of what you know today.
it's like starting at 0, 2, 5.
Uh-huh.
Okay.
It's
Yeah, okay, so yeah, this will be the integral from 0 to 5, and 0 to 5 represent my beginning interval and my ending, the beginning of the interval and the end of the interval, right? And then R of t represents the rate, and which is, in this case, it's also the height of the rectangle. D of t is the change in time, and so that represents the width of the rectangle. I'm trying to think, do I want to write that in here, or do I have it somewhere else? I have it somewhere else also, but I have this here. I'm going to you can put yours down on your actual location. I just don't have room. So notation I have this as T naught as the beginning time, and this as T of F as in the final time. Okay. This rate right here, this is your rate, R of t, and it's going to end up being the height. Whereas the D of t, think about it being the change in time, and it is your width. So what this is this is the height of the rectangle times the width of the rectangle. And so we're finding the area there. Let's see, do I have anything else?
I'm sorry, guys.
It's okay.
You had to get up at a decent time today.
I drank an energy drink this morning, and I
Okay.
tried to like drink it out with water, and I was bouncing off the walls.
Oh, she
second
was
and third hour.
skipping down the whole way.
I'm skipping down the hallway.
Okay, top of the next page.
She's so tired.
So I kind of talked about how those were right Riemann sums or right-hand rectangles. So we've got some options here, and I'll give you some vocabulary here. But this first set, okay, one way you could look at these is these are left endpoint, okay, because those rectangles on the left side of the rectangle is where it touches the curves, right? So those rectangles are drawn to touch the curve at the left. They are also, if you're ever asked to do lower rectangles, they are lower rectangles because they are beneath the curve, okay, as opposed to these, which are not beneath the curve, so they're lower. And inscribed, when you inscribe something, it is inside the shape, right? When something is inscribed inside of something, it's inside the shape. And so these rectangles are all inside the curve. In other words, under the curve. Okay? Let's see. If we find the area of those rectangles, we're not going to, but if we were to find the area of those rectangles, would it be an overestimate or an underestimate?
Under, because it's under the line.
Because they're under the line, right? So the point that I'm making there is it's underestimating. And in general, what I'm saying here is the left endpoints are going to underestimate anytime it is an increasing function. Okay, so this is going to be underestimating on increasing function. Now, this next picture represents right endpoint rectangles. That's what we used on the previous page, right? They're right endpoint. They are upper sum because the rectangles are above the graph. And they are circumscribed. That means they are outside of the graph, right? We drew those rectangles outside the graph, and so they are circumscribed, okay? Under or overestimate? It's going to be an overestimate. And in this scenario, anytime you're on an increasing function, right? These are all examples of increasing functions. It's going to be an overestimate there. Trying to get you guys thinking about the idea of under and overestimate again. It's an overestimate on an increasing function.
This would be an under on a decreasing function.
Mm-hmm. Yeah, because if you change this to a decreasing function, and these are you're using right-hand endpoints, then they end up
So
below
it'd
it.
be
It all depends on.
over on decreasing is what Doug said, right?
Mm-hmm. Okay. Midpoint. Okay. You always prefer when it's the nice left or right endpoints because it's just a little bit easier to work with. But we also sometimes see the midpoint, as in right here. This essentially is like the idea of 0 to 4, right? I mean, I know it's not labeled, but that's what our brains are probably telling us, is it's 0 to 4. And if we're told to use 4 intervals, well, we usually use either the left-hand endpoints or the right-hand endpoints. Well, there's also an option of using the midpoints, okay? And that is going to be more, when you use the midpoints, you're going to be finding more of the average, okay? You don't necessarily think of it as an over or under estimate. We're going to think of it as a more precise estimate. It's not necessarily exact yet, but it's going to be more precise. So this one ends up being an average of your upper and lower sums. Okay, a little bit of notation before we look down at the bottom. Let f be continuous on the interval a to b, and f of x greater than or equal to 0 for all x in the interval. Let a to b be partitioned into n subintervals of equal length, where delta x is defined to be b minus a over n. Then the definite integral of f over the integral a to b, is given by. Now, you've kind of got two things happening here. Okay? This is our fancy limit notation. And more of what, when we talk Riemann sums, which is what we're talking today, that you see. What you need to be seeing here is that this f of c of k, kind of like what we were doing on the other page, that's going to represent the height of the rectangle. Delta x, the change in x, is going to represent the width of the rectangle. Okay. You are familiar with the E or no?
It means
The
sum of all
summation.
the numbers.
Summation.
Summation notation is what that is.
Yes. Zero.
Okay. Yeah. So that sum, that means the sum from k equals 1 to n. Where here, notice it's the limit as n approaches infinity. Okay. So that is, we see that a little bit, but
I
Yes.
don't know if you already explained this. What is the k equals 1? I'm sorry.
that's just your starting point.
Started that, and then
You go to n, but in this case, it's the limit as n approaches infinity, which means you're going infinitely. It's not
Okay.
something you're doing by hand, in other words.
okay,
Okay.
This is like reminding me of chemistry.
and then I still don't get the e. I'm like, is that just saying the beginning point and where you're going?
Mhm.
Okay.
And it's saying you add. So kind of like what did we do on that last one? We took the area of the first rectangle plus the area of the second rectangle. We kept adding them, right?
Mm-hmm.
And so we did the sum from we essentially did the sum from k equals 1 to 5 because we did the first 5 rectangles.
Okay.
Okay? And we are plugging in 1, 2, 3, 4, and 5. So this is saying you plug in 1 plus you plug in 2 plus you plug in 3 plus, and you just to wherever it tells you to end.
Okay.
Okay?
It's just like they're really complicated.
The basics are not. But we probably, if you haven't seen the basics, it seems a little more complicated. So
So what's C?
Good question. What is c?
it would be some value.
Is it
I wanna-
given?
No, it's going to be some value in the interval from A to B, but they don't ever specify that, do they? Well, it's going to represent. It's going to represent. So think about this. It's C of 1, C of 2. So it's like the first number, or the first interval breakup plus the next interval plus the next interval. And so it's that C of K is breaking into, so like, here's C of 1, C of 2, C of 3, C of 4, whatever yours is. In other words, this is a general. We don't have it, it's not specific to a specific formula or anything. That is just your general right there.
Oh, so that's kind of whatever
Whatever you're
k
plugging in.
is.
Like y1, y2.
Yeah. Okay. Now, eventually, this is our integral notation that we're going to get to. And this is going to be more this is what you're going to have to work with every day. The integral from a to b, and then of f of x times d of x. Okay. And again, we'll go into that a lot more later on. Okay. Give us, I don't remember exactly how many lessons, but
I'd rather do derivatives.
Give
me the derivative
Okay.
of polynomial.
Okay. General solution method for inscribed or circumscribed rectangles, lower or upper sum. Now, I don't think we even use it to the next page, though. Yeah. Draw a rough graph of the function over the interval. Use the formula, delta x equals b minus a over n, to determine each subinterval length. In other words, if you're finding the area from 0 to 20, and they want you to have 5 intervals. I know that's an easy one I just gave. But this is a formula to help you determine how long the intervals are. Okay? Compute x coordinates of the rectangles, either at left end or right end. Compute the areas of the rectangle. So that's once you have the x interval, the x values, we'll plug them in to get our y values. Kind of like it's what we just did here. We had our x values, then we plugged them in to get our y values, right? So like right here, let me make sure you realize this. When we plugged in 1 and got that 2.296, what is that? That is the height of that rectangle, yes? Then we plugged in 2. We got 4.243. That's the height of that rectangle. Now, each of these rectangles were only 1 wide, right? So 1 times 2.296 was that first one. This had a width of 1 times 4.243, okay? So each time you're finding the value you're plugging in times the height, okay? And again, we're going to do examples, I promise. And then you'll find the sum of all the different areas,
Which
okay?
is the E, right?
Yeah, I don't know how much we're actually using E in our notation. We just more write it out, but yeah. Okay, now, example 3. Find the area A under the graph of f of x equals 1/2 x plus 1 on the interval 0 to 5 using geometry. So forget this for a moment. They're taking us a different way for a moment. Find the area.
Oh, that's easy. Triangle.
What'd you say?
Never mind. You can make a triangle and a rectangle. Right? Like make a horizontal line or one.
What are we doing? We're doing from 0 to 5, yes? So we're doing that piece there. Could you do a triangle and a rectangle?
I'm not seeing where you're getting the triangle.
I see it. You
One.
put a line, horizontal line at 1.
1 to 5.
Oh.
I'll be honest, not the direction I was going to take us,
I was-
because I needed to
What direction were you
review
gonna take
something
us?
else. What is this overall big shape?
Trapezoid.
Trapezoid.
I'd rather do a trapezoid because I don't remember the formula for that.
Well, and that's why I think here, I'm going to erase this in a moment. So if you see a rectangle and a triangle, can you guys all confidently do a rectangle and a triangle?
Base
No.
times sine.
1/2.
Triangle is 1/2 bases.
Yeah, I feel confident that you guys can get that one, down. I want to talk about a trapezoid.
But you don't even have the definite height for a triangle.
Is that 1/2 base 1 plus base 2 times height?
A trapezoid's like,
I thought a trapezoid looked like this.
a trapezoid's like this.
It can. Okay. So Sophie, you're visualizing
Yes.
that. Okay, so the definition of a trapezoid is, I don't have this precise definition, but it's a 4-sided object, right?
Mhm.
With one set of parallel sides.
Oh.
Oh.
So this trapezoid is now on its side,
Yeah.
right?
Yeah.
Squished.
So you're taking, horribly drawn, but
Get the gist.
I got
if we take this and we stand it up,
Yeah.
okay, are we there now with trapezoid?
Yes.
Okay.
Welcome to calculus class.
Okay, and I wish I would have drawn that a little bit better, but that will still help us. Now, with this in mind, okay, what was that area?
Is it 1/2 base 1 plus base 2 times height?
Mm-hmm.
Whoa.
Well, wait, how did you say that?
Base 1 plus base 2 times height.
Okay. I say 1/2 times height times base 1 plus base 2. Fine. You just put your height. I'm assuming your base 1 plus base 2 is in parentheses.
Yeah.
Now, to get this information, we need to figure out some pieces here. We need to know base 1, base 2, and the height.
Or 1, 2. I'd say 3.5 for base 2. Height is 5.
Yep, I say 3.5 too.
Okay, where's the height of 5? Let me take that one first.
0 to 5.
0 to 5.
Okay, so right here, from here to here is my height, yes?
Oh,
So we can all agree height is 5. I know, I have to take this into pieces so we can all see it, don't I? Okay. Let's talk, I believe Kylie is calling this one
base 1.
base 1. So in other words here's height. She's calling this one base 1. What do you know about base 1?
It's 1.
It's 1. Now, what is that in terms of this function here? Because I think we're forgetting we have this function here, right? It's- Does that intersect exactly at 1?
Yes.
Yes, because it's when you plug in what?
0.
0. So officially, if you do f of 0 and you plug in 0, what do you get? 1/2 times 0 is
0.
0 plus 1.
You guys got really lucky. Yes.
So f of 0 is 1. And so I can agree that base 1 is 1. Now, we were guessing on base 2. How do we verify base 2?
Plug 5 in there.
You're plugging 5 in. Good. So f of 5, half of 5 is 2.5, plus 1 is 3.5. And so that is indeed base 2.
Then we plug it all in.
All right to go, yes? 1/2 times 5 times 1 plus 3.5. I have 7 halves written in my notes actually, but. Whatever 2.5 times 4.5 is.
11.25.
11.25 what?
Units?
Units squared.
Because it's area units squared. And that was finding what? That was finding
Oh, okay.
this area right here, yes?
I remember when that's simple. It's gonna be straight.
This is fun.
Okay. Moving on. Oh, the next page does talk about red and blue. You can use red and blue. You can just use 2 different colors if you want. It's whatever you want to do. I guess I probably have.
I forgot my crayons and all.
There's colored pencils here if you want them, or just use 2 different colors, or don't even use 2 different colors. It doesn't matter.
What were the colors? Red and blue?
Red and blue is what it says, but it's, you know, make it work how you want. What is the first one? The first one's blue. I'm going to use
Can we use this sharpener?
this blue.
The sharpener
Yeah.
we used for last time?
I got you.
It should work. Okay.
Like you was still crisp enough.
I'm lighter, you just thought.
Okay, for the function shown at the right, draw rectangles forming the left-hand sum, shaded in blue. Which I'm going to more outline them in blue than as opposed to shading because we also have to do red rectangles on here later, and I can't do that with a BenQ. So, left-hand rectangles. Now, wait, for the function shown at right, draw rectangles forming the left-hand sum, shaded in blue. And it does say let delta x equal 2. So what delta x is what?
Change in X.
It's a change in x. It is the width of each rectangle. They didn't really tell us this up in the beginning, but each rectangle needs to be 2 wide, left-hand rectangles. Where are these left-hand rectangles going to be?
Above.
So right here, the one, I guess, okay, I forgot, there's points here. We're using the points. So if we're using the points here, we're going to make a rectangle that from 8, since it's left, this is the left-hand edge of the rectangle. And there's one rectangle. Okay? Huh?
Thank you.
Now, that's a width of 2. My next rectangle starts at 2. 2 intersects this graph at 7. It's a left-hand rectangle. So where am I going to draw this rectangle? This is the left edge, and now I'm going to draw to the,
And it's supposed to be in blue still?
these are all blue.
Well, mine's aqua
Is that a problem, Mario?
Yeah, it is.
Okay. And then left-hand rectangle starting at 4. It's going to start at the point 4, 5. Go over 2 and drop down. And we're stopping there because we don't have enough of the graph to go any farther. Okay. Calculate the left-hand sum. Okay. Now, I'm going to say LH for left-hand sum. How many rectangles did I end up with? 3. So I'm going to say LH3. What do you know about all 3 of these rectangles? They all have a width of 2, yes? So they're all going to be 2 times some height, right? So what's often done here is you'll see it as 2, because that's your delta x, your width, times, and then we'll do the heights and add those up. What's the height of the first one?
8.
8. So for this first one, we're going to do 2 times 8, right?
Yeah.
Or in other words, just 8. What's the height of the next one?
7.
So that's going to be a width of 2 times a height of 7. And what's the height of the last one?
5.
5. So it's a width of 2 and a height of 5. So I have my 2 out front here. And then in my parentheses, I can say 8 plus 7 plus 5. Do you see mathematically how that works out? As opposed to me doing 2 times 8 plus 2 times 7 plus 2 times 5, I can do 2 times the sum of 8 plus 7 plus 5.
Really?
And we get 40.
It is 40.
We're going to,
Yes.
this is, I'm jumping ahead, but is this an over or under estimate?
Over.
The rectangles are over the curve, yes? So we know the area under this curve is less than 40. Don't exactly know what, but because this is an overestimate. Okay, change colors. Next, draw the rectangles that represent the right-hand sum, shade them in red, and calculate the approximate area under the curve given the right hand. Now, with the right hand, is there a rectangle I draw from here? No, because I can't, that needs to be a right-hand edge, and I can't go this way, can I? So we're not going to use that point this time. What about this one? Can I draw something with a right-hand edge? Yeah, what do? We draw over to 7. And you have that piece there. Are you seeing it? Now I go down to the point that is at right here. Yes? If I'm making a right-hand edge, where am I going? It's going right over there.
These feel like huge underestimates.
Yeah, those were kind of big overestimates. So,
I know.
and then last one, this one right here. It's going to be that little tiny piece, yes? Now, what do you know? The first rectangle had a width of 2 and a height of what? 7. The second rectangle, width of 2, height of 5. Last rectangle, width of 2, height of 1. As a shortcut here, since they all had the same width of 2, you can say 2 times the sum,
7 plus 5 plus 1.
which is 2 times 13, 26.
You didn't give me a chance to think about
Is that an overestimate or underestimate?
Underestimate.
It is an underestimate because those rectangles are clearly below. Now, I believe I've answered part C. Which sum overestimates, which sum underestimates. The overestimate was the left hand. The underestimate was the right hand. We've already talked about that. I was just jumping ahead because it's easier to do it when you're in the flow of the problem and you don't have all the crazy rectangles staring at you at once, right? Now, D. I don't know if we can get through this today or not, but we'll see. Repeat steps A through C for the function shown at right. Let delta x equal 0.5.
But it's still 2 units. So at least there's that.
Okay, so we're going back to blue. And blue is our left-hand ones. They say the width is 0.5, but are you guys with Kylie and what she pointed out? The width is 0.5, but it's still 2 blocks, isn't it? because 0 to 0.5 is labeled as 2.
Is units an okay word for that though? Like if you're just thinking about it in your head.
I don't know. I don't know if I want to say that or not, but I knew what you meant.
Okay.
Okay, so what are we supposed to be doing? Left hand. So what's the first left hand? We go right here at 0, 1, over, and you have that little rectangle right there, yes?
Mm-hmm.
Then you take this next point. It's a left hand, so we're going to go over towards the right and draw the rectangle, yes? Are we catching on all right? Because it's hard for me to explain this.
Yes.
Okay. And then the last one, left hand, looks like that, right? Okay. Each of these were 0.5. This first one is going to be 0.5 times the height of 1, 0.5 times the height of 4, and 0.5 times the height of 6. So I can say 0.5 times 1 plus 4 plus 6. And that ends up being 5.5. My brain said 11 halves, so yes.
Would you still put
Yeah. At the time, my brain didn't say 3 because I hadn't looked far enough
Where
ahead.
does the 3 come from? The
But
blocks?
There's 3
Oh,
rectangles.
okay.
Under or overestimate?
Under.
This time it's an under, isn't it? Okay. Change to red. We've got to do right hand. Okay. Dang it. So close. Right hand. You can finish right hand tomorrow when you walk in. How's that?
Can we put our colored pencils in our little, like, turn-in?
Sure. You don't want mixed in? Okay. Well, I really hope to finish that. We'll finish that tomorrow when we come in. Hopefully this slide will still be here so I can make some connections as we fill in that chart at the bottom of the page. So.